Hello everyone, welcome to today's lecture on quantum computing. Today we will look into some more sophisticated algorithms for gate model quantum computers and again see how these in theory can outperform classical computers. What we will start with today is a simple searching problem. You may have heard of Grover's search, so that is something we will look into later. So we'll start with a simpler search algorithm today, which just shows how we can query again a set of functions. So again, we're given an oracle and we want to understand what function in that case specifically is executed. So remember last time we looked into Deutsch's algorithm. Deutsch's algorithm allowed us to distinguish between two sets of functions. So we were able to understand if we are given four functions, which set the one function that is given in my oracle, to which set it belongs. So if we split that into two sets, okay? Today we will specifically find out what function exactly it is that we're running. And for today, suppose we're given a simple function of the form f of 0, 1, and we have two input bits and we produce one output bit. So we have an input register of 2 bits and we write into an output register of 1 bit. And we have four functions. We have the function, let's call it 0, 0. Or let's write it that way. So let's say we have the inputs 0, 0, 0, 1, 1, 0, 1, 1. And then we have the function 0, 0 here. And the function 0, 0 produces the output 1 given 0, 0 and produces 0 anywhere else. Then we have a second function, let's call it 0, 1, which produces the output value 1 given the input 0, 1 and 0 everywhere else. Then we have a third function, let's call it 1, 0. You get it. And 1, 1. Okay, so we are given these four functions. And now the goal is to determine which one it is that that is represented in our oracle. Again, we don't know, so it's like in Deutsch's algorithm before. In other words, the function takes the value 1 on one input and 0 on all the others, and we want to find out which function it is, or which input it is that the function takes the value 1 and therefore are able to conclude back which function it is that is executed by our oracles. When we do that classically, we always assume it's the worst case that we're trying. So the worst case would require us to do 3 queries. So 3 queries are necessary and sufficient to solve the problem. In the quantum case, again, 1 query will be sufficient. And I'll show you how to do that. So at first, I'll write that down as a circuit diagram so you see what's happening. So we start with 2 definite input states, 0 and 0. And then we also have 1 other bit that we give the value 1 at the beginning. What happens then is that we apply Hadamard's. You know, the Hadamard transformation, so again, distinguishing between 0 and 1. The only difference is the relative phase. So this one creates a superposition that is 1 over the square root of 2 times 0 plus 1. And that one does 1 over the square root of 2 times 0 minus 1, okay? What happens here is that we execute our oracle. Let's call it B of f this time. So this is our function. What we can do then, so you just take that as granted for now, and I'll show you how it works in a bit. So this one, we don't need anymore. We make this a garbage bit. We throw it away. But then here, we're not done. Here we have to apply a very specific unitary transformation before we measure that system. So we will also look into what that is exactly and how we learn more about it. So, but let's start at the very beginning. At the very beginning, so we take our two input states, and so you remember if we apply Hadamard transformation, so again, let's call our state psi. If we apply our Hadamard transformation to the first two here, then remember we have 1 over 2 plus 0, 0 plus 0, 1, 1, 0 plus 1, 1. And here we have our state 1, which becomes 1 over square root of 2, 0 minus 1. I will continue here, but let's just have a look. So for the sake of writing and using the space optimally, I will continue in that form, but let's just multiply that out for a moment and see what happens. So if we do that multiplication, our whole state becomes zero, 1, 0. It's important that we talk about that too, because we're using something that's called phase kickback, which we have also already used in Deutsch's algorithm, as you may have noticed. But let me explain that in a second. And here we have plus 1, 1, 0 minus 1, 1, 1. Okay, so that's that multiplication executed. And so let's assume we run F00. So our oracle here is given or represents F00. What would happen then? So what would happen is that for the state or for the input 0, 0 here, we would get this result, okay? For the input 0, 1, we would get that one here. For the input 1, 0, we would get that one here. And for the input 1, 1, we would get that one here. So one thing that I want you to notice here is the relative phase. So this relative phase here for the state or for the result where we get 1 is negative. For all the others, it's positive. And what we've done here, so you'll see if you execute the F01, then let's look at it quickly. 0, 1, 1. Let's see what 0, 1, 1 is. 0, 1, 1 for F01 would also be negative. So you see, for any of these where you see a 1 here, the phase would be negative here. And that's important. And that comes from that second qubit here, or the third qubit here, sorry. Here we have that negative phase, and it's called phase kickback. So we use this register, or this qubit, to kick the phase back to the states where it matters. Okay. So I will now use a different way of writing this down. So let's say we apply this, then after this transformation B of F is performed, then the state would become, let's say we apply B of F to psi here. So after we perform this transformation, we have 1/2 minus 1 power of f(0, 0, 0, 0). And you see, this is another way of writing things. So because if you have, so that result here, f(0, 0), if we, so f(0, 0) means in that case, the input is 0, 0. That doesn't mean it's that function. But let's assume it is that function here. Then it would produce 1, which will be minus 1 to the power of 1, which has a negative phase here. So it would be negative 0, 0 in that case. Okay, so and that's what's important here. That's the same phase kickback effect that we have seen here. I just leave that one out. So actually I execute it on this 3-qubit state, and then I separate again. So that I can move that into trash. I don't need that anymore. So then for the next one, again, we would have minus 1 to the power of f of 0, 1, 0, 1, plus 1 over 2 times minus 1 f of 1, 0, plus 1 over 2 minus 1 f of 1, 1, 1, 1. Okay, so we have that, and still, so as I separate again, I take that one, minus 1, and that goes to trash. So we don't need that anymore. All right, so we are left with this here. And you may give it a try again. So if you have, so let's say we have the second one here, f(0, 1), this function. Give it the input 0, 1. We're here now. So f of 0, 1 equals 1. So minus 1 to the power of 1. It's minus 1, so we have the negative phase here. And if we do it with the first one, so again, let's say it's f(0, 1), and we feed it 0, 0, then the result is minus 1 to the power of 0, which is 1, results in 0, 0 being positive, okay? So anytime we produce 1, we will have a negative phase for the respective state here, okay? Now we don't need that anymore. So, and now, of course, for all of these 4, we will have different phases here. Let's write that down quickly. Different relative phases. So let's say it is f of 0, 0. Then the result will be 1 over 2 minus 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. If it's f of 0, 1, okay? So we get these 4 different outputs depending on which function it is, okay? And there is something special, like with the Deutsch algorithm before, something special about these four states. Deutsch algorithm didn't exactly produce four orthogonal states, but so for these four states, we have four orthogonal states, orthogonal set. So this means they're unit vectors and they're pairwise orthogonal to each other. Okay. And whenever it is that you have an orthonormal set like this, it is always possible to build a quantum circuit that exactly distinguishes the states. So in fact, the corresponding unitary transformation is easy to obtain. You just let the vectors from the columns of a matrix and then take the conjugate transform. The matrix here, so if you just look at that, would look like, so we have 1/2 here. So then it's summarize that as a matrix. Let me just do that. It's easier to write. You get that matrix. Okay, looks exactly like our four states that we want to hear. So this is the transformation that we obtain. And actually, this is the transformation that we're applying here. And I leave that to you to verify, but you remember you can always construct such things out of gates, and we want to add that to the circuit here. So in that case, the gate representation looks slightly more complicated than that matrix representation, but it's not too tough. So you remember the phase flip or the Z operation that we had, which is just, so just write that down, the Z matrix here. It looks like identity, but not precisely. It flips the relative phase here, okay? And for representing this one as a set of gates that you want to see or you can see in your circuits, then you want to write down, let's say it's for these first ones, okay? So I just draw the B of F here again. And then we continue here. This one went to trash. We apply two more Hadamarts here, followed by Z operations. So it's the phase flip operations, followed by a controlled phase flip operation.
I couldn't find followed by controlled, but here it's other music by control.
Sorry, Alexa has also something to say. And here we have the controlled Z operation. And then we go on and do two more Hadamarts. And then we measure the system. And after we measure the system, we will see that depending on which function we have here, the output of these two bits here corresponds to whatever function has been executed. Okay, so therefore, with just one call, with just representing the whole thing as a set of transformations, we were able, instead of using 3 calls, just by doing one call, find out which of the following 4 functions, of these 4 functions, our oracle represents. I recommend trying it out yourself, playing around a little with these gates to get some familiarity. But you'll see, so this is actually one of the algorithms, so we're getting closer towards practical application. That makes sense. So with Deutsch's algorithm, you don't see practical application immediately. Here it becomes easier because this is search. And we will learn about more complex search in a bit. The next algorithm that we will look into is called the Deutsch-Josa algorithm, which is a generalization of Deutsch's algorithm to multiple qubits. The Deutsch-Josa algorithm, which is a generalization of Deutsch's algorithm to n input bits. What we want to do is we want to determine whether a function is constant or balanced. So again, our oracle implements specific function, but this time we don't want to find out to which set our function belongs, like in the original Deutsch algorithm. We rather want to find out about whether the function is constant, which means for each of the inputs provided, it produces the same output, or if it's balanced, which means for half of the inputs, it produces 0. In that case, we only have one output bit, or for the other half, it produces 1. So it means if a function is balanced, let's say you have 10 inputs, then for 5 it will produce 1, for 5 it will produce 0. And that's what we want to find out. And ideally, we only do that in one call. With a classical computer, it's again a little more complex. We are not allowed to have any failure, so that's one of the constraints. And that means for the query complexity, it means it's 2 to the power of n minus 1 plus 1, which just says we have to try it out on every input. Let's say we have 10 inputs again. And even if we're good and we tried it with 8 and half of the time, so 4 times we get 0 and half of the time, 4 times we get 1, and for the last 2, everything may change. We may get 2 1s, and instead of ending with a balanced function, we will have a function that gives us 6 times 1 and 4 times 0. So it's not balanced then. But here, it's either constant or balanced, okay? So that's one thing to know. So for the classical Deutsch-Josa, we can query 2 different random values. If we say we have a bounded error, we can just query 2 and we can guess it's constant if the same output is produced. If it's not, then we can guess the function is balanced. And the probability, so of course, for failure, as it's written down here, it's 2 to the power of n minus 1 over 2 to the power of n minus 1. So smaller than 1/2. Okay, so this is the bounded error classical query complexity. For the quantum Deutsch-Josa, if you look at that circuit that we see here, so we have n input bits, so x is part of a string of length n, and now we have 1 output bit. And we again use the phase kickback that we used before. So remember, the phase kickback means if we just have 1 output bit here or one qubit here, and can be a trash qubit and auxiliary bit. So if we put that in a superposition, we have that negative relative phase that we can use in our phase kickback or as a phase kickback bit. So this is the trick 1 that we apply. If you look at the second equation here, we have our x input bits, and we have, so this x means it is of length n. I forgot the n here. So it's not just 1. So that means we have that plus that superposition with negative relative phase. Then after that, we apply our unitary transformation, which is the function. And then we do something else. So we'll look into that in a bit. But concluding or summing up, that just says if it is 0, our function, then the phase remains positive. If it is 1, the phase becomes negative. And the function in that case is computed into the phase. So if you look at the last line on the slides here, you see after applying the transformation u of f, so which is the unitary of that function that we are applying, we again have that notation here where we say minus 1 to the power of that function. So if the function produces 0, f of x is 0, then the result will be positive phase, okay? But again, so this is just different way of writing, and we get rid of that bit again. So it's just something that we want to use. And the second trick, which is not really a trick, you already know, that is just we are operating on Hadamard bits, so which means on superposition. And that, again, allows us to evaluate every possible input at once, which is one of the remarkable strengths of quantum computers anyway. So if you're able to allow an algorithm to evaluate all possible configurations of the system, so therefore all possible inputs of a problem maybe at once, this is where a lot of the speed comes from, the conceived speed up. All right, so if we put that together, then we leverage that phase kickback, and here again you see that notation, so in the line on the right, so we have the current state after applying the transformation u of f, which is just depending on whatever input the function or output the function gives you, provides us with, we'll have a different phase here. And then what it means is we put the function in the phase. So we'll see this is the phase and the function is in the phase. So the function gives us the phase in that case. And so when the function is constant and balanced, you see some slight differences here. But that's just what we just had here before in more mathematical detail. Please feel free to go over that. The summary of that is that if you, after applying that unitary transformation u of f, if you again apply your Hadamard transformations and then measure the system, you will have a result string, and the result string R, it will always be 0 if the function is constant in that algorithm, and if it's balanced, it is never 0. Okay, so therefore, with one call, again, we did something that a quantum computer, a classical computer, would only be able to do in 2 to the power of n minus 1 plus 1 calls. So in our worst case scenario. One other algorithm that we want to have a look at is a Bernstein-Vajirani algorithm. And it's a different kind of problem. So again, we're given a function with n bit strings as input and 1 bit as an output. So that remains the same. However, the function, when you look at it here in the second equation, is given by a times x and addition modulo 2b. Okay, so or x or b in that case. And here is another way of writing that down, but we're interested in finding that string a, whatever that string a is, a bit string of length n is, okay? And b in that case is just either 0 or 1, so it's not of length n, or n in that case is 1. So querying the function f yields a single bit of information, but we need n bits of information to describe a, so therefore it's the bounded classical error complexity is omega of n in that case. So in the classical Bernstein-Vajirani algorithm, you remember Deutsch's algorithm, Deutsch user algorithm from before, it looks very similar to how we start. So again, we have our input register, we apply our Hadamards here, we have our 1 qubit that is in the state 1, from the input state 1, apply Hadamard. So again, we want to leverage our phase kickback. And here is, so what happens after applying the Hadamard transformations in more detail. We don't need to go over that, so I think we did Hadamards often enough. So that shouldn't come as a surprise. And we can determine A, again, with only one single query, okay? So the only difference in that case in our algorithm is the transformation u of f. Everything else is identical to the algorithm that we just learned about before, the Deutsch user algorithm. So not too much of a difference. The challenge is always how to come up with a circuit for an algorithm, given some inputs and outputs, for example. What's the optimal circuit to do that? Okay. There's some more information about Bernstein-Vajirani. And here we have Simon's algorithm. Simon's algorithm is also particularly interested. It's about the hidden abelian subgroup problem, and that may have applications in cryptography. So that's something that we also want to have a look at. So we're again getting closer to practical application. And please go over Simon's algorithm. It's not too much of a difference and not too many news in here to the things we already learned about. Please go over Simon's algorithm yourself. And we'll talk about two more algorithms, the classical quantum algorithms that are very interesting, which are Grover's search and Shor's algorithm. Two of the most prominent algorithms in the quantum computing community have been both developed in the 90s. And the first one we will have a look at is Grover's search algorithm. It's named after Love Grover, the guy who came up with it, working at Bell Labs back then. And the promise is simple. So it's very often it's called a database search algorithm, which it not really is. So in reality, it's a function inversion algorithm. So that's more accurate. But we'll see in a bit why it's called database search. So the promise is, or the problem is, given a function f of x mapping n bits to 1 bit. So again, we have n input bits and 1 output bit. Determine the value of x. So what's the input? Such that f of x equals 1. So find the one entry in the database that equals 1 for f of x. So we have a promise that this value is unique. I know very often this is compared to, let's look at a phone book, and I have a couple names and numbers, and you want to find the number to a name or the name to a number or whatever, then you could query this a lot faster. But I don't want to compare it to a database search, since if we had an unstructured database, the oracle must at least be of linear complexity. So this is not something we can use for querying an unstructured database. However, since we want to find the one value where f of x equals 1, or the one entry, this is sometimes called database search. On top, we have a promise that the value is unique. There is a generalization of this algorithm that can evaluate a database. I will still call it database, but it will evaluate a database where you have multiple true entries for f of x. So that's also possible. And classically, if we look at this problem, we would need to evaluate O of n values. Let's say it has 1 million entries. Then with the big O notation, we always assume the worst case. So in the worst case, to find my one entry, I would have to do 1 million queries to that oracle. And Grover's algorithm enables a search with O squared of n, which is, let's say, again, 1 million entries. I can do it with 1,000 queries. And this quantum algorithm itself has two crucial steps. It calculates the function on all these values simultaneously. So let's call this function u of omega. And the second one is reflection about the equal superposition state. So we will do a reflection. You remember the reflection operators that we talked about. And this is the second step. So, and this is an iterative algorithm. So we repeat this O of square root of n times. And let's look at that first transformation in more detail. So let's say I have u omega, and I apply that to x. Then the result is minus x if omega equals x. Okay, so let's say if omega equals x, which means f of x equals 1. Also, when I apply u of omega to x and the result equals x, then it is because omega does not equal x, therefore f of x equals 0. Another way of writing this would be, again, taking u of omega x, and let's say we have auxiliary bits, which we will also see in that circuit diagram that I have on my following slides. Then the result would be x in that case. So if we have x and y here, result would be x, not y. Again, if omega equals x, which means f of x equals 1. And same for the application on x, y. So the result will be x, y if omega does not equal x, and therefore f of x equals 0. And one last way or generalization of this would be, so let's say I have u of omega on x and y, then you could say, as we learned before already, the result is x, y, XOR f of x, controlled not. So much to that. This is our transformation u of omega. Sorry, there's a pop-up came up here. And we start in the state of, so as you can see in the slides, the state S, which is 1 over the square root of n, so our number of bits, inputs, in the superposition state. So repeat the following square root of n times, so the application of u of omega, which we see here, and then the reflection operation, which is described here as u of s, and then the outer product of whatever s is, minus I. So in the system then will be in the state omega such that f of omega equals 1. So if you end up doing it for 1 million entries database, you do it 1,000 times, you end up doing that. But how do we perform US? First, we invert the operation that prepares S, which is just Hadamard's on all qubits. And then we reflect about 0. For example, apply to the outer product of that 0 minus I, and just to remember how you calculate that. So you have your column vector here, and you have your row vector here, your bra, which is that one. So, and if you execute that, this is the result matrix of this one here, right? So this is how you apply it. And lastly, repeat the operation that prepares S. So all that you can see here in that Grover diffusion operator. This is what it's called in the circuit diagram. And then the Hadamards denoted here in that case with n just means we do a Hadamard, so superposition of n bits. Okay, so if it's 2 bits, then this would be 2. And this whole thing we repeat square root of n times. Here you can see in more detail what the reflection does. And I think it's always good to look at it graphically. So I have my graphics here. So let's take the example where n equals 4. So we have 4 different inputs and the solution x is 3. So 3 is the database entry that we want to find. And we will start in the state of S. So this is the starting state. So remember when we write down our superposition state in that form, or as it is here, 1, 2, 3, 4, then this just means the first one for 2 qubits is 0, 0, the second one is 0, 1, 1, 0, 1, 1. Okay, that's how it works. So we apply the function u of f, giving us that result. So u of f in that case, so is our u of omega here. And then the mean of that is 1/4, so easily calculable. So if you have that result here, the 1/4 times 1/2 plus 1/2 minus 1/2 plus 1/2 equals a quarter, so 1/4. And graphically, what you can see down here, what this means is we apply the reflection operation u of s. The result will be 3, so the desired state that we're looking for. Okay, so and you see you increase the probability of measuring the system in that state, so of getting that result. Another example, so if we take n equals 1 with the solution 6, then reflect the target like we did before in the previous slide, then the result is 7/27th, and then reflect about the mean, reflect target again, the mean is 17, 243, and you can see for the result being 6, how it changes, right? So the probability increases for the result of 6 being measured. Okay, reflecting about the mean, solution with high probability. Keep in mind that still, although we can be fairly certain that this result will be measured, a quantum computer is always a probabilistic device. So it's the solution with a very high probability. So it doesn't equal 1. Probability doesn't equal 1 to measure the system in that state. It's close to 1 if you do it right. So another way of looking at the whole thing is rotations. So we define the ket perpendicular to omega, which is given by that equation that you can see here. And as you know, reflections can be executed via sine and cosine, so trigonometric functions. Here you see the angle. So the phi here represents the angle. So cosine phi of s and cosine sine phi of s of omega gives you the angle of rotation. Okay. And the u of f reflects omega and leaves all orthogonal states unchanged. So that means there's a very important sentence here. We still have orthogonality, which is the requirement for us to be able to distinguish between the states that we have in the system. So it's important when you measure the system, and it's important when you run operations on your superposition state. Okay. Here's more detail on the reflection operations, rotations. I'll skip over that. I think, again, it may help to look at it graphically. So you see what every iteration, every Grover iteration, let's call it that, gives you. So where you can see the application of u of s and u of f, so our function plus the reflection, and we do it again and we do it again. So, and therefore approach that state, the final result that we measure. So depending on how many entries you have, that's square root of these entries. The number of these entries is how often you have to do that, okay? And that's where you end up in your desired state. So I always have an easier time imagining or keeping this picture in mind where we just do these reflections. So the function application followed by the reflection and rotation. What about multiple targets? Possible too, but in general, this works exactly the same. This is Grover's search algorithm. So keep in mind, I would not call it a database search per se, although when we describe it, when people talk about it, it is called a database search, but it is not. In reality, it's a function inversion, and it's not possible to perform any better in that case. So this is the fastest you can go with the search algorithms through an unstructured database. Okay. All right. The next thing we will have a closer look at is quantum Fourier transform. And so you know Fourier transform. Imagine you have, well, let's start differently. We will look at this quantum Fourier transform because for the next algorithm that we will try to understand, it's Shor's algorithm, it's essential. So it is based on a half classical part, but then the quantum Fourier transform is a very important part of that algorithm. So you may have heard about Shor's algorithm. It's the one that allows you to factorize primes. So you can factorize numbers into primes. So you can find the prime factors of any numbers. And classical encryption algorithms, such as RSA, they're based on the promise that this is a very difficult problem and cannot be achieved easily with a classical computer. But it turns out with Shor's algorithm, you can do it. And here's how that goes. So let's talk about the Fourier transform first. So let's say we have a smoothie. That's always a good example. how do you find the recipe? So you have the final product, but what's in it? And you may have some filters that you want to apply. So let's say you have the banana filters, you have the orange filter, you have the milk filter, you have the water filters. And so what we want to do is apply each of these filters on my smoothie. So let's say the smoothie equals a signal. I apply a filter on that smoothie, and then I find out how much of each component, or in terms of a signal, how much of each frequency component is contained in the smoothie. Okay, and we can so reverse engineer the whole, so all of the ingredients of that smoothie. So there are a couple of caveats though that we need to um, consider. So one is that filters must be independent. So the banana filter needs to capture bananas and nothing else. Same for a signal. If I have a specific signal that I want to catch or a frequency component, then I only want to have a filter that filters for that specific frequency component and not for um, a couple others. So it doesn't overlap with other filters. The filters must be complete. We won't get the complete recipe. So if we talk about smoothies again, if we leave out a filter, so there is something missing then, right? So that's the same with the frequency analysis that we do. And the ingredients must be combinable. Smoothies can be separated and recombined without issue, but the ingredients, when separated and combined in any order, should give us the very same smoothie again. And this is also what we're looking for in a signal. If we have a signal and we analyze it into its components, then recombining these components must give us the very same signal again. If it does not, then we know something is missing or we did something wrong. Here is more information on the Fourier transform. So, but basically, it is what I just told you. It is the decomposition of a signal into its components. And so it's one of the most useful mathematical tools in modern science. It's amongst many other things used for removing noise from data. It's used for examining the properties of crystals. It is used for producing holograms, what we can see here, and is especially useful when we have something with underlying periodicity. So imagine that sine wave that we have here in the picture with a bit of frequency noise. So that's very important if we can get the clean signal. So if we remove the high frequency components, in that case the noise, then we get the clear signal. Okay, so this is the clean set of data. And usually when you do a prediction, let's say you have some time series and you want to analyze that time series, be it sensor data from vehicles, be it whatever else. So, and you have that time series, then you want to get rid of the noise and you want to use the clean signal to make a prediction. There are other things you have to worry about, like seasonality, but then if you want to get rid of that noise first, that's the most important thing, okay? So, but then here we want to find or what the Fourier transform allows us to do, and that's important for Shor's algorithm. It allows us to extract the periodic behavior of a function. So it can be used for period finding, and that's the basis for Shor's algorithm. And how we use that in quantum Fourier transform, we'll see in a bit, but that's the most important part. The period of a function is just its recurrence, right? So when does it come back to its initial peak? So what's the period to complete one circle? Um, and what we will look at is the DFT, or discrete Fourier transform, which is a Fourier transform that just works on discrete data. So as you can see here in my slides, it looks rather formidable, but it's not so much. So it's not too complicated at all. Let's say we want to analyze for the frequency component k here, then we say y k equals 1 over the square root of n, so how many signals you have at all. Then you have the xj, which are complex numbers, and you have the exponent here. So you have e to the power of 2 pi a k over n, and that's just all constants plus the signals that you want to use and the frequency you want to analyze for, okay? I think it is always good to look at an example. So let's say we have a signal. We have xj given with 1 and 2. So we want to calculate yk, okay? So for x0, we start with x0 is 1 and x1 equals 2. So that means we have n of 2, so 1 over the square root of n is 1 over the square root of 2. And we start with the frequency components too. So in that case, for k equals 0, so that's what we want to analyze, and k equals 1. We want to see how that goes. So and you just plug in the values. So y of 0, which means k equals 0. So which means that exponent on the right, you can also plug in 0 for that, and which gives you 0 in that case. Then you see the result is just 1 over the square root of 2 plus 2 over the square root of 2 equals 3 over the square root of 2. And for k equals 1, same procedure here, except that you will not get rid of that whole exponent here. So you will have 1 plus 2 e to the power of I, okay, because k equals 1 in that case. And so that's the result that it gives you, and the result then is minus 1 over the square root of 2. So for both components, k equals 0 and k equals 1, you have analyzed the signal, which was given by 1 and 2, and that's the result that you see here. So it's all in all, it's not too complicated. The formula looks complicated, but it's just plugging in. It's not that difficult. Since our state vectors for qubits are just vectors of complex numbers, we shouldn't be surprised that the Fourier transform can be applied to the state vector as follows. So the DFT of the state can be outputted. So if we have our superposition here, so again, you remember you have that column vector on the right with A0 to A n minus 1. These are your amplitudes that we will look at. And the J's are your states, so the possible states of the system. Then we'll look at that in more detail. So the DFT of the state can be computed as f of psi, so if we call our state psi, equals bk to k, and then we analyze what our bk is. It's the Fourier transform that we just did before in the previous slide, so nothing changed here. But again, let's look at an example. I think that helps. And you remember well that superposition state of 2 qubits, which in that case is given by 4 amplitudes and the basis states. So you have the amplitudes A00 to A11, and the same for the basis states. And that's what we're going to analyze in that case. So we're just plugging in, and so n equals 4 in that case. Okay. Since we have 1 over the square root of n, this becomes 1/2. And we go from 0 to 3, which means we have our 4 inputs that we consider. And if you just plug it in and analyze for 0, 1, 2, 3, you get these results here. Okay, this is how you want to write down in quantum form with amplitudes that you don't know that Fourier transformation. So it's the exact same procedure that we had before. You can try and plug in and reproduce this formulae, but it's really not difficult. It's just plugging in. And so let's create a unitary out of that, so the quantum Fourier transform. Let's look at how we can construct a unitary out of this. So we write omega equals pi I over so e to the power of pi I over 2, and noting that if you take that to the 4th power, it's e to the power of 2 pi I, which is 1. Okay, so and when you look back, so I will just, hop back to that original calculation. So we want to create a unitary out of that. So look at the signal B0 here. So you have the amplitudes A00, 01, 10, 11. And you don't have any other amplitude before, so which means you have all ones. Okay, so the first line that you see here is all ones. So let's go back again. Let's look at the signal B1. So here you have, when you look at it, 1 e to the power of I pi over 2. Then you have, I need to get a little closer, e to the power of I pi and you have e to the power of 3i pi over 2. Okay, when you plug that in again, this is the result. So you have omega squared, omega to the power 3. And then you do that for the rest of the signals. So for 1 and for 2, you do the very same. For 2 and for 3, sorry. And then, noting that omega to the fourth power equals 1, you can, and omega, so if if you take e to the power of 9i pi over 2 is the same as e to the power of pi I over 2, that equals I. So then you can plug in the results here, and on the right you see the Fourier transform. And this can easily be shown, and again, please feel free to try. This can be shown to be a unitary operator, so you know how you can verify if it's a unitary operator. So you check the operator, and here we have nice complex numbers in it too. So you take its complex conjugate transpose, and then you multiply it by it, and if the result is identity, then you know it's a unitary operator. So you can build a fairly simple circuit that performs this transformation. So now I have an operator that does the quantum Fourier transform. It's quite simple, but has an additional gate that you see here. It's the controlled RK gate. It's a rotation gate here. And you just see the phase angle on the right bottom is e to the power of 2 pi I over 2 to the power of k. And it's a controlled gate, as I said. So if the control bit is 1, it's executed. If not, it's not executed and leaves as the state as it is. Then what you also need to do is a swap gate, implement a swap gate on 3 qubits in that case. So the swap gate, as you remember, it swaps on 3 qubits, so it swaps the bits. And that's also easily done. So you remember how you want to construct such a gate. So let's say you have an input state of 1, 0, and what you want to produce is a state that is 0, 1 in that case. So you swap these two, then you create, you just take the column vector here, 0, 1 in that case, and here you have a row vector. Sorry, 0, 1 in that case is 1 here, 0 here, and 1, 0 is 0, 0, 1, 0. And you multiply that out and get a matrix, and you do that for all the transformations that you see here. And if you did that, you just add all the matrices together, and then you get that big matrix that you see here. So that's how you get to that. And now the circuit performing the whole quantum Fourier transform is as follows. So it has our Hadamard transformation well known. It has a rotation that we just saw before. And that's it. That's the quantum Fourier transform. Here's a 2-qubit quantum Fourier transform. No key information left here. Yeah. Very good. So now that you understand how to implement the quantum Fourier transform, we want to have a look at Shor's algorithm, which is one of the most important algorithms, arguably, in quantum computing. So Shor's algorithm is a factoring algorithm. It is difficult, so you want to decompose a number into its prime factors. Feel free to try that out and find efficient algorithms classically, but you will see soon that it is very difficult to find the prime factors of a number. Okay. So what we want to have a look at here, let's just go over that. What we want to do is start with period finding. Okay, period finding is what we just learned to do with the quantum Fourier transform or Fourier transform. And you'll see it here. So on the bottom of that slide, you can see a signal, and you can see the recurring components. And that means that is the period that we want to find and analyze. And the key insights that Shor used is that period finding can be performed efficiently on a quantum computer, and it can be used to factor integers. So that's important. So these two things are the most important insights that Shor provided in terms of his algorithm. So what we want to do is we have a number n on a quantum computer, and we want to factor that. So what we do is we select x coprime to n and use the quantum computer to find the period of f of s. So this is our signal, and say x to the power of x modulo n, the number n that we want to analyze. And we use the order of x to compute possible factors of n and check if they work. If not, then we just rerun the whole algorithm. Okay. A very early result already in 2001, so it's 18 years old, is or has been obtained by or was obtained by IBM, and they showed that they can factor the number 15. It was not very impressive because right now our keys have 256 or even up to 1024 bits. But in that case, they were able to factor the number 15 into its prime factors. But what they showed was that it works on a quantum computer. And an important thing is that the RSA crypto system, so this is one of the most commonly used algorithms for encrypting communication, relies on our inability to find the prime factors of very large numbers. And so there are two classes basically of encryption or cryptography, so that we consider to be important. So one is symmetric, and one is asymmetric. And the asymmetric one, that is the one that's important. For symmetric, if you want to find the key, so there is a key that's used for both encryption and decryption. So it's the same. You want to use Grover's algorithm, which is significantly faster than any other algorithm. But if you want to do or look at asymmetric encryption, then what you do is you have a public key. That's the one that is available to everyone. So it's used for encryption. And then you have a private key. And the private key is specific to each person. So you cannot use the public key to decrypt an encrypted message anymore. You have to have a valid private key. And I may have a private key to decrypt a message. And where this is important is for all the browser-based communication that we use for HTTPS, for example. If we do banking online, then that's the algorithm, public key infrastructure, that's what's used. And for this, it is important or dangerous. Not now, we know that. We know that today there is no quantum computer that can crack these algorithms efficiently, this encryption efficiently, but at some point we will have them. And this is why we have to worry about this today. There are no classical algorithms known that can do this efficiently. And the best one is the number field sieve, which factors a number n in the time that you see here in the computational complexity. So, which is exponential in n, and is impossible to factor even modest number, making RSA still very secure. But Shor's algorithm can factor n, and what you see, it's O of n squared log n log n operations, so which is significantly faster than the fastest classical algorithm. So it's exponentially faster. And factoring now, so all of a sudden becomes a tractable problem. It's solvable on a significantly powerful fault-tolerant quantum computer. And the key idea, as I said before, that underlies Shor's algorithm is that of period finding. And suppose we're given a function f of x equals f of x plus r, for example, a sine wave, and is said to have a period r. And classically, finding this period r is very hard. All we can do is test the function at many different places and find the period in this way. And a quantum computer can do a lot better than that, which makes period finding a lot easier. So let's look at how we find the period r of a function. So we start off 2-qubit registers of the size n. So remember, when we have registers, could write them down here, a register of n qubits doing something, right? And then you have another register in that case that is also of the size n, so large enough to hold some number of n. And then we prepare some number n. So the number n is not the number of inputs in that case, it's the number that we want to analyze. So we prepare these states in state zero. So that means we start in the zero state, and the composite system then is in the state that you can see here, 0, 0, but of n qubits. And first we want to apply the quantum Fourier transform that we just constructed before to the first register. And the state after the application of that quantum Fourier transform, as you can see here, is so only to the first qubit applied gives you value of x in the first qubit register, and 0 still is in the zero state. Oh, the second qubit register is still in the zero state. And omega is 2 to the power of n, depending on the number of qubits that you have, okay? Now, that state, let's call it psi again, we operate on it with some unitary operator, calculating f of x and putting that into the second register. So f of x, you remember, is our period finding. So we add that to the second register. So our first one is still in that state after application of the Fourier transform, and the second one is now in the state f of x. And the total state of the system is now the second equation that you can see here. So again, first one in the state x after application of the Fourier transform, and second one after application of our unitary the f of x transformation is in the state f of x. So what happened here is that f of x for all 2 to the power of n values of x has been calculated at once. For 100 qubits, this is 2 to the power of 100 calculations in parallel. If you have a system that has thousands of qubits, let's say 5,000, then you would have 2 to the power of 5,000 computations in parallel. That's a lot. And so here again, you see one of these remarkable powers of a quantum computer. Anytime you add only one bit, you double the computational power. So it's an exponential increase. Okay. So the thing is, there is still the caveat of measurement. When you look at the system, so looking at the system, depending on how you implement it, either by interacting with magnetic fields or using polarized laser light, causes a collapse, a decoherence. So the system will collapse from this rich superposition into a definite state. So you cannot observe all the results. You only get one definite result. So still, we want to measure the system, although we lose a lot. So making the second, the measurement on the second register gives the answer now that f of x equals u. So whatever that u is, so that second register must collapse onto the state u, and the first register must collapse into a superposition of all values which give f of x equals u, right? Because these are correlated. So we want to see that anytime I measure u, only those results in the first register remain that are, let's say, in the same line, if you want to look at it that way, as our u. So the contents of that first register are periodic. So when we apply, so periodic means, yeah, you know what periodic means. We just talked about it before. So apply a QFT to obtain the spectrum. So the spectrum is that what we analyze. So we and again do the quantum Fourier transform. Looks formidable again, but it isn't, as we learned. It's the same operation that we just did before. And it follows that this is the result. So from that, it's easy to deduce R as long as J and R in that equation have no common factors. So if they do have common factors, the algorithm does fail, and we must run it again and hope for better luck. So we can use a quantum computer to measure the period of a function. Okay, that's the most important result here. And the last one, so please also read that last sentence here. So choose f of x equals a to the power of x modulo n, where n is the number that we want to factor. And a should be smaller than n, of course. Then the period r can be used to find the prime factors of n. And you may choose randomly. So stages of Shor's algorithm to find, to go through are: if n is even, return a factor of 2, and determine whether n equals y to the power of b for integers, y greater than b greater than 2, and if so, return y. Yeah, and you see how the period is calculated. And we know that for stages 1 and 2 in that algorithm, we have classical algorithms. For stages 3, 4, 5, we don't. Okay, and now again, it's time for an example. So we are in the need of showing this as always. So and I will try it with a factor, with factoring the number 39. Okay. So first, we want to make sure that we cannot do this classically very efficiently. So it's not even, and so therefore it cannot be written as y to the power of b for integers and y and b. So we cannot factor 9 classically efficiently. That's the proof for that. So that's the test you want to do. We choose a randomly. So we choose a equals 7 so that the greatest common denominator here of a and n equals 1. So that's the test you want to do. Choose a so that the GCD is of a and n is 1. So we choose n equals 10 so that the register is big enough to hold that number. And note that the bigger n we choose, the greater the accuracy of our calculations will be. But in reality, that's also limited by our hardware. Okay, so you cannot use more qubits than you have to your avail on your chip. And right now, with gate model chips, we are in the range of the 70s. Not high quality, so I would say rather more in the range of the 50s today. So again, initially we start with our state psi in the state 0, 0, apply the QFT to the first register, and now compute the f of x function, which is f of x is a to the power of x modulo n, and put the result into the second register. So that's our unitary that we execute. So we have again what we just saw before, the result of the QFT on the first register in the first register, and the result of the function in the second register. And let's look at that in more detail. So the values of f of x in that case are depending on where you are. So if you have 0, it's 1. If you have 1, it's 7. If you have 2, it's 10, and so on. And in fact, it's quite easy to see that since we're looking for r, that the period in that case is 12. Why so? Because if you look at the first one, 0 gives you 1, and 12 again gives you 1. So this is the recurrence of the signal. So this is where we find periodicity. Okay. Let's continue. Anyway, so because this is not something we know, this is just something for demonstration here. So we will continue the algorithm and measure f of x and say that f of x is 22. Then we apply the inverse. Quantum Fourier transform leads to a probability distribution of possible measurements on the first qubit. And that's the probability distribution. So a highly likely measurement is y equals 85. And we continue here. Remember that measuring the first register will give you that state that you see here. And you execute the steps. So here is step 5 of Shor's algorithm. So we notice that R is even, and then you do these computations as specified here, and finally compute the greatest common denominator from of a to the power of r half plus 1 and n, and gives you the result 3. So you have 3 and 13, that's 39. The prime factors. That's it. So now you understood Shor's algorithm. I have here some additional remarks. There are some more remarks on universal quantum computing, which I want you to go through. That's the last lecture on algorithms today. The next time we will look into quantum annealing and how quantum annealing works, because all that we talked about up until today is gate model quantum computing. And quantum annealing is this other architecture that works slightly different. So it's only suitable for optimization problems and sampling tasks, but still we know that a lot of the problems in real world can be converted in such problems. So therefore, it is very valuable. It's the biggest system size that we have today with currently little more than 2,000 qubits. I say a little more because it cannot always be said exactly how many qubits one system has because of manufacturing problems. But then we will expect about 5,000 qubits still this year. And this gives us, so in theory, a solution space of 2 to the power of 5,000, which is fairly big that we can evaluate with that system. And that's why it's exciting. Thank you very much for today.